Okay, today we are going to define the different gas laws that look at how pressure, volume, and temperature are related to each other. So let's go through each relationship. To begin with, we're going to look at the pressure-volume relationship. So basically, when we have a fixed amount of gas, meaning we don't change the number of moles, a decrease in volume will increase pressure. Why does that happen? Well, if we look at our little diagram here, if the number of moles stays the same, but they're in a smaller container, then they're going to collide with the walls more often. So this means pressure and volume are inversely related. When the volume goes down, the pressure goes up. When the volume goes up, the pressure goes down. When we look at the temperature-volume relationship, if we have a fixed amount of gas at a constant pressure, and that's the key to this relationship is the constant pressure, an increase in temperature will increase the volume of the container. So when we increase the temperature, the particles are going to have more kinetic energy, they're going to move faster, they're going to collide more often. So if we want to keep that pressure constant, then the container has to expand to keep the number of collisions the same. So you can see this happening when you have a balloon and you take it outside into the warm air outside. It's going to expand because we want to keep the pressure the same, so those particles moving faster at a higher temperature have to expand the container to keep the same number of collisions. So when temperature goes up, volume goes up. Temperature goes down, volume goes down, so they are directly related. Now, when we have a fixed volume, so this time the container can't change its volume, an increase in temperature will increase the pressure of the gas because when the particles are moving faster, they're going to collide more often since the volume of the container won't change. So temperature and pressure are directly related. When one goes up, the other one goes up. So we can put these all together in what's called the combined gas law. And the way we look at the combined gas law is this. P1 V1 over T1 equals P2 V2 over T2. So basically, this is how we're going to look at when we change one of our variables, how does it affect the other variables. Now, the good thing about this particular formula is if part of it is held constant, for example, if the temperature doesn't change, then you can take the temperature out of both parts and just use P1 V1 equals P2 V2. Or if the volume is held constant, you can take out the V's and just use the P's and the T's. Now the 1 and 2 represent the initial pressure, volume, and temperature, and the 2 represents the final pressure, volume, and temperature. So let's look at how one of these calculations works. A sample of gas occupies a volume of 7.50 liters at 0.988 atmospheres and 28 degrees Celsius. Calculate the pressure of the gas if its volume is decreased to 4.89 liters while temperature is held constant. All right, so temperature is held constant means we can take out the T's. So we're just going to use P1 V1 equals P2 V2. So we need to go through and define all of our variables and then plug them in and solve for the one we don't know. So our initial volume, which is V1, is 7.50 liters, and its initial pressure, P1, is 0.988 atmospheres. And those are both units that we want, so we don't have to do any conversions there. We want to calculate the pressure, so we're looking for P2 if its volume is decreased to 4.89 liters. Okay, so we have the units that we want, liters and atmospheres, they're the same on both sides, so we can plug them in to our formula and solve for P2. So 7.50 liters times 0.988 atmospheres equals P2 times 4.89 liters. Right. Okay, so when we solve for P2, we get 1.52 atmospheres. Now, does that make sense? We decreased the volume So should the pressure have increased? Yes, it should have. So that makes sense with our calculations. Okay, the next gas law we're going to look at is called the ideal gas law. In this particular gas law, nothing is changing. It's just a certain set of conditions for an ideal gas. So basically, it's the pressure, the volume, the number of moles, and the temperature of that gas all at the same time. So we're not changing anything here. We're going to solve for one of those four variables. Now our formula for the ideal gas law, PV equals nRT. Okay, so P for pressure, V for volume, N for number of moles, and T for temperature. Okay, now those units, liters, volume, atmospheres for pressure, moles for N, and Kelvin for temperature. So those are the units that we need, and if we don't have those units, we have to change them. Now, let's talk about R. R is called the ideal gas constant, and it equals 0.0821 liters atmospheres over moles Kelvin. Basically, these units are all going to cancel as you solve, so you're going to get the units that you want. So basically, you just need to know R equals 0.0821. Okay, so let's do some examples with PV equals nRT. Here we go. Carbon dioxide is collected in a 250 milliliter flask after decomposition reaction. The pressure of the gas is 1.3 atmospheres at 31 degrees Celsius. How many moles of CO2 were generated? All right, so let's write the variables we know. So our volume is 250 milliliters. The pressure, 1.3 atmospheres. The temperature, 31 degrees Celsius. How many moles? So moles are the one we're trying to find. All right. Now, we have some conversions here to do because we don't have the right units. So 250 milliliters, if you convert to liters, 0.25 liters. Atmospheres is good. We want Kelvin, so add 273 and you get 304 Kelvin. Okay, now we can solve for moles. So, pressure, 1.3 atmospheres. Volume, 0.25 liters, equals N times R, 0.0821, times temperature. Okay. Now, all of our units are going to cancel with the units in R except for moles, so our answer will be in moles. So when we do the algebra, we solve for moles, and we get 0.013 moles of CO2. Now, we've seen before, if we know moles, maybe the question asks how many grams of CO2, so we can convert from moles to grams. Or how many molecules of CO2, we could convert from moles to molecules. So you could be asked to go a step further, but that's how you use PV equals nRT. All right, so one more example. This time we're going to apply the ideal gas law. Airbags in cars are inflated by nitrogen gas generated by the rapid decomposition of sodium azide, which is NaN3. And here's our balanced equation. If an airbag has a volume of 36 liters and is to be filled with nitrogen gas at a pressure of 1.15 atmospheres at a temperature of 26.0 degrees Celsius, how many grams of NaN3 must be decomposed? All right, so let's start with what we know. We know that our volume is 36 liters, our pressure 1.15 atmospheres, and our temperature is 26.0 degrees Celsius. Again, we have to change that to Kelvin, so 299.0 Kelvin. Liters are good, atmospheres are good. Now, we don't know N, so that's what we're solving for. Now, these variables are all for nitrogen gas, which is right here. Okay, so we're solving for moles of nitrogen gas. PV equals nRT. All right, pressure, 1.15. Volume, 36. N.0821 times temperature, 299.0. So when we solve for N and we keep the two sig figs from the volume, we get 1.7 moles of N2. All right, now, is that answering the question? The question says how many grams of NaN3? That's over here. So, how do we get from moles of a product to grams of a reactant? We use stoichiometry, exactly. So, we take what we're given, which is our moles, so 1.7 moles of N2 over 1. Now, we already have moles, so we go directly to the next step, which is mole ratio. 3 moles of N2 on the bottom, 2 moles of NaN3 on the top. Okay, so our moles cancel. Now, we're still trying to get grams over here, so we need to find the molar mass of NaN3. When you look on the periodic table and add them all together, you get 64.99 grams of NaN3 per mole. So our moles cancel. And now, when we do our final calculation using our stoichiometry, we get 74 grams of NaN3. So that's what you would find in an airbag that would need to decompose to make the nitrogen to fill up the airbag to make sure your face doesn't hit the steering wheel. So that's what gas laws look like, and we're going to be practicing all of these gas laws the next 2 days in class. So make sure you bring your calculators and your periodic tables, and we'll figure all of this stuff out.